good to see all of you here. Like Matthijs just said, my name is Vera and this is Rick. We are colleagues and we work at Pippel. And for the past 2 years, I've been working on a project which had to do with 3D objects. And we used Python to do this. That's why we're here today, obviously. And for the last half year, Rick joined us and he did a more research-intensive part of the project. Oh, you can still join us. And today's talk will focus mostly on the research that Rick has been doing, as it's quite innovative and the most interesting thing. Yeah, thank you. Like the title says, we're working with 3D objects, and we want to make a prediction with that. And this is a field of research that it's not much research in. And there is a lot of research in a 2D setting. So 2D would be images. There's a lot of neural networks that can work with images. However, not a lot that work with 3D objects. So that's what made this project so interesting. Well, I think most of you know what 3D objects are. We come into contact with those when we're really young. Maybe you had a tool that looked like that. And you quickly learned that you cannot fit a round shape into the square hole and the other way around. So you quickly learned that different 3D objects have different properties. Then we get a bit older, you probably went to high school and you got into contact with those kind of objects. And yeah, you didn't have to fit them in the right hole, but you had to calculate the shape, the area, and stuff like that. And at least for me, at this point, I didn't come into contact with 3D objects a lot. I mean, of course, everything is a 3D object. I just didn't have to calculate anything about that. Until our next project, or this project we have been working on. And this is just an example of what 3D objects look when you load it in Python. We started this project, and this was the first time I had to program with these kind of objects, so it was all new to me, and I hope it is also for you, so I can teach you something today. And we're at PyData, so it's focused on how we did that using Python. During our project, we have been using two libraries mainly. First, we used TryMesh, and secondly, we used Open3D. And during the project, we used both of them in parallel, because TryMesh has some functionalities that Open3D does not, and the other way around. So we had to switch between the two to do everything we wanted. Yeah, thank you for joining. We just started, and we just gave an introduction about the 3D objects.
Hi.
When our project continued, we noticed that most of the functionalities of Open3D were the ones we needed, so we gravitated more to Open3D, and now we don't use TryMesh at all. When using this library, of course, you need 3D objects, and those have specific file types. I asked ChatGPT what kind of file types you have for 3D data. Apparently, there's a lot. And that's not really relevant for today. So we'll focus on the data we had, which are STL files. And as you can read, it's not that interesting, but the description says that STL files are mainly used when doing 3D printing, which is also one of the use cases of our clients. So they have to 3D print the project they manufacture, and that's the reason why they have their files in an STL file type. And that's the reason that we got it as an STL file. Well, it's PyData. I want to show some code. So I'm going to show you how you load your 3D object, your STL file, into Python. It's really impressive. You load your data, or you import your library, and then you do read triangle mesh and your file name, and you get a mesh object. And a mesh object is something I didn't mention yet, so that's what we're going to do now. So this is how you read it. And then in Open3D, there are multiple ways to show your 3D object. So one of them is a mesh, and there are several others. And the different types have different properties and can be used in different kinds of modeling, and are good for some use cases and bad for others. So this is the first. This is a mesh. And a mesh is basically a group of points connected by triangles. So the official name is a triangle mesh, but in short, just mesh. And you can see that in the image, so points connected by triangles. And the pros of this type of 3D object is that you can capture a lot of surface detail, and it gives a quite realistic representation of your object. And this is why it's also used a lot in gaming, because it makes it's good for rendering. I don't know. I'm not into gaming that much, but it's used a lot in gaming. Downside is that file sizes get quite large, and it comes with a lot of processing complexity because the points are connected by triangles, so everything depends on other points as well. So the second type of data is a bit simpler. It's a point cloud, and the name says most of it. It's a cloud made up of points, and in this case, the points are not connected to each other. So it's a more simple way to show your data, and it's unstructured because the points are just like they are x, y, z coordinates, so they are not dependent on the other points at all. Downsides are it's harder to capture all the surface detail unless you get a really big number of points, but of course if you get more points you have to have more calculating power. Lastly, we have a voxel grid, and a voxel grid, it looks really ugly right now, but that's why I have a better example. You can think of a voxel grid the same as that you do a pixel grid if you were to work with images. So that looks like this. So if you have an image of a dog and you make that a pixel grid, it would look like the thing on the left. If you want to do it in 3D, you just add another dimension and you get a voxel grid. The plus sides of this are that because the structure is really similar to that of images, a lot of the models that work on images can be translated to a 3D setting. You just have to adjust for the extra dimension. But that's a really big plus side of the voxel grid. Downsides, however, and the image shows it already, is that your resolution is worse, and it struggles to get your surface detail correctly because it's all made of blocks and not of more. It cannot make a more round surface. Well, these are the basics of the 3D programming, and I want to illustrate the use case we've been working on. I have to note that it's confidential, the true use case. That's why we are working with the monkeys. That's not our true data set. But for the points we want to make during this talk, it doesn't really matter if it's monkeys or cars or any other thing. So I mentioned this before. If you were to show this monkey as a voxel grid, then you can use prediction techniques that are also used on images quite well. And one of the things that works quite well on images is classifying what's shown on the image. And this can be done for 3D objects quite good as well. So if I were to give this object to a model and ask, is it a monkey or a seal or an elephant? That's something that is already pretty far developed in 3D world, let's say. So this is not something we have been doing, but it's something that can be done quite, not easily, but rather easily. We have been doing something different. We have data of monkeys of 5 years ago, and we have data of monkeys, the same monkeys, 5 years later. And what happens to a monkey in 5 years? It grows, just like a human does. So in our example monkey, he got a mustache, he became broader, he has a thing on the back of his head, and he developed a double chin. So those are changes that can happen, okay, probably not, but that can happen to a monkey in 5 years. And the goal of our research was, can we predict that? So given a monkey that looks like this right now, can we accurately predict what the monkey will look like in 5 years? So we have to predict how all those points within the monkey will shift over 5 years and where they will be in 5 years. And that's something that, was not researched a lot. And there are multiple reasons. One of the reasons being that a data set like this, so you have monkeys of 5 years ago and monkeys now, that's not a data set that's readily available. If you go to Kaggle and you look for a data set like this, you probably won't find it. And that limits the research that has been done on this subject. And furthermore, it's a pretty specific use case, so I think that also doesn't help with people wanting to research it. However, we had to do that, and I've been working on a different part of the project, but Rick has been doing this, so he will tell you more about this.
Yes. Yes, thank you. Okay, and I just quickly want to mention, if you guys have questions in the meantime, just raise your hand. You don't have to wait for the end, of course. Okay, so now that we know what objects we are looking at, so we are looking at these monkeys for now. They have some local transformations. And we also, what we will do is we will represent these monkeys using point clouds. So we use these set of points to actually represent them. And then there are possible ways on how you could potentially map such a transformation. But what we will look at today is set-to-set mapping. As we have this, on one hand you have the untransformed object, and you have a lot of points on them, and you want to find the counterparts on the transformed object, and with the idea that those points would be located at the same position if there would not have been any transformation. And then if you know these differences, you can compute those and then eventually model these. So that's the idea on how we want to model these predictions. So let's get into it. You load your data in, and it looks like this. So this is the point cloud representation of the monkey. You can see it is nicely centered around the origin. What happens if we load in another one? Then you can see that things go wrong. And even if we add in another monkey, you can see they are not nicely aligned with each other. And this actually makes it difficult, and scenarios like this can occur because usually you use sensors to actually acquire these the data. But it could be that because you're measuring objects over time, it could be that you have a slight orientation within your scanner, and then scenarios like this can occur. And of course this is a very exaggerated example, but already small differences can cause troubles, because we want to predict using these coordinate values. So if all the monkeys would have a completely different orientation in space, different point would refer to a different area, so it would be difficult to not only do forecasting but also to do something like classification. So another example where you can see why it's relevant to have first all the objects aligned. So this is a 2D example, 2D image, and then the left one you see the objects are nicely aligned, and this is not the case for the right one. And if you want to model this transformation by mapping points, for example, you can see that in this figure you have fewer points that actually need to be offset to actually result to the transformed object. Well, it would probably be also possible on the right figure. It would just take more time because there are more points that needs to be offset. So it will also make life easier to actually align these objects. So we need to do some pre-processing steps on these 3D images. And these are so-called isometric transformations that we need to remove. And examples of them are, for example, translation. Well, that's pretty easy to resolve because you can just center a point cloud. Let's say that we are not dealing with reflection for now. You can have a difference in scale. That could be part of the transformation that you want to model, but it could also be that you want to rescale your objects. So let's leave that for now. And then on the other hand, you can have this, you have this rotation, and that's not so easy to resolve actually. So for this, we need to rely on specific techniques, and these are called point set registration techniques. And what you do there is you have a source object and a target object, and what you want to do is you want to align the source object with the target object. So in our case, the target object is the specific orientation of the monkey, and as you can see, the source is slightly rotated, so the objects are not nicely aligned. So we need to align them, and we can do this by relying on algorithms. So one of the most known algorithms is this so-called ICP algorithm, and what they do there is they find correspondences of points on both objects. And if you remember correctly, we also need those later to actually map the transformation, so it's already helpful to have them as well. So it will first find these correspondences on both objects, and that's usually done by using distance metrics. And then when you have these correspondences, you have a second step, and there you try to optimize an objective function. And you do that usually, the objective function is usually the sum distances of these correspondences. And so you eventually apply rotations to your objects so to minimize that criteria. So I can see maybe some difficult faces now, so it's always nice to look at an example. So here we have actually 4 points, but you can only see 2 because they are on top of each other, and so these are these correspondences. If we expand them, you can see it better. And you can see that these correspondences do not refer to the exact same area. So that's first you detect these correspondences, you apply a rotation, so to minimize distances, and also because there will be non-overlapping regions, you will always be able to improve. So You rotate this, and then you iteratively do this. So again, you try to find correspondences, and they already refer to the better locations. Apply another step, and eventually you will have the objects aligned. So this is kind of the idea behind these algorithms. But you can already probably imagine that things will go wrong if your object is, for example, 180 degrees rotated, because then it will be difficult to actually match these correct correspondences. And in those cases, you will often converge towards some sort of local minimum where you will not get the objects aligned. So for this, we actually need to rely on a different version of the algorithm, but what is important here is they use, instead of using distances to match points, they use specifically called post-invariant features. So you look at specific features that are always the same, despite the orientation of your points. So by actually looking at neighboring points, you can get features, and so it considers kind of like neighboring points. You get a specific feature, and then it doesn't matter if the object is rotated, because you would get the same value in that position. And in that way, you will be able to match these correspondences. And if you match them correctly, you will be able to actually align the objects. But of course, because we had PyData, we also want to show some Python code. So here you can see an example of what that would look like. And this relies on then this open 3D package. So it has a lot. Oh yeah.
Question just out of interest: how far would you get if you would just do PCA on this point cloud? Would that get you most of the way there, or?
You mean really for like aligning the objects, or just?
Yeah, for aligning like principal components.
Yeah, I think that could also be an idea to.
Are they not rigid?
I wouldn't really know. We haven't really looked into that. Also because a lot of these algorithms have already been implemented. But I can imagine that a tool like PCA would also work. But the nice thing about this is that a lot has already been researched and implemented. So for example, by using this open 3D package, you can, as you can see, with basically two functions. So the first one extracts these features that I talked about. Don't get lost in this slide. Then in the second function, you actually apply the registration, and you can see that just with a few lines of code, you can already align these objects. So it's not really difficult. You can just rely on these packages. So that also shows that it's really easy to get started, and so to encourage all of you to, after today, start working with 3D objects. But you can also see it's not that easy, because there are quite some high parameter values. And so, yeah, you need to know what you're doing, and you need to experiment a little bit with these techniques. So this is then what it would look like if you align the objects. And as you can see, now they are nicely aligned. So this is this pre-processing step that we need to solve. And now we can actually move on. Yeah?
Is there like a global optimization when you apply all of these transformations, or is it a greedy fashion? Like at this moment, what's the best transformation to apply?
So this one, for example, this ICP algorithm, this one is just it has a closed form solution. So you can actually get the values by using I think principal component analysis and eigenvalues and those kind of things. So I think that's a good one, because it actually relies on these techniques. And in that way, you can just compute a closed form solution, and you iteratively do this. So again, especially because ICP is a local algorithm, you can converge in a local setting. So in that way, it's greedy, as you cannot always get an optimal solution. But then again, this other step, fast global, is more of a global approach, and then you often have a higher chance of actually reaching a global optimum. So yeah, I hope that answered your question. Yeah. Okay, so now that we have the objects aligned, these pre-processing steps, we can move on to why you guys are actually here. So how to use these point clouds in 3D modeling. And as Vera said, there have already been some networks like three-dimensional convolutional neural networks that have been applied to voxel grids, because they have this regular structure. Makes it very easy to directly apply networks. But again, voxels, they are memory intensive, hard to work with. So what people often also do is they project data. So you have this 3D point cloud, you project it to a 2D dimension, and then you apply 2D models, because there are just more models available for that. But then again, it's also difficult because what projection technique do you use? From which angle do you actually project? So that also presents a lot of difficulties. So we don't want to step away from this point cloud representation. We actually want to use this one because it's close to raw data. We don't want to convert it to another type. But yet we cannot directly apply these networks to point clouds. And the reason why is because point clouds have an irregular structure. And so what this means, I can best illustrate this with an example. So again, you have two monkeys, two objects, and you represent them by a set of points. And if you look at the first point in your set, it will maybe refer to the same area. But if you look at the second point, it could be that it's located in a different area. And so if you do this for all points, you can see that there can be some inconsistent ordering. Even if you align objects in which you use these pre-processing techniques where you match correspondences, and you can get some of them in a consistent order, but you will never be able to match all of them correctly. So you have this inconsistent ordering. And as we know, neural networks are permutation invariant. So that means that if you present a different input or sequence to it, it will also give you a different output value. So if you would think, for example, if you want to predict house prices, you have these input features like number of bedrooms and those kind of things. If you would randomly switch the order of these variables, you will get a completely different output every time. And also when you train a network and you alter the input every time, it doesn't really make sense. But this is actually the case for point clouds because we cannot get them in a sequential ordering. So actually to resolve this, we can use a clever trick that is called using symmetric functions. And basically with these functions you take the maximum, these functions suggest the maximum or the sum, where you always get the same value despite the order that you present to it. So if you would have, for example, 5 points, and you would take the maximum for each point, across all the points you will always get the same value, and it doesn't matter what the order of the points is. And so by using these tricks, it doesn't matter what the order of the input actually is. But again, if you would apply this directly to your point cloud data, you have x, y, z variables, 3 dimensions. If you apply such a symmetric functions, you just get 3 values. That doesn't really say much. So first we want to extract more features out of the point cloud. And a possible idea on how you can do that is to present them through a neural network. You learn a higher dimensional feature representation. And then you apply these symmetric functions per feature. And so in that way, you actually end up with so first you map each point independently through a network. There's an input size of 3 and a higher dimensional output value. You do that for all the points, you get some sort of feature map, and if you then apply these symmetric functions, you get some sort of global feature vector that represents your object. And then it doesn't matter what input order you provided to it. So you will always get the same output value. And so in this way, you actually get a representation for your point cloud, for the object, that actually resolves this permutation invariant issue. And so in that way, we could use these features for any task we would like. So we could, for example, add a classification component, but we could also do forecasting, for example. This is maybe in short what it looks like, because I can think that's a bit abstract if you have 3-dimensional points and you map them to a higher dimensional feature space. So just to quickly illustrate what this actually does, let's consider a simple feature map where you just only have 5 points and 3 features. Then if we isolate on a specific feature, you can basically see this as a function of the points and you get specific values. If you would then plot these points with red being a high activation value and blue being a low value, you would get something like this. And if you have a lot of features, you have a lot of these overlapping regions across your object. And if you would then apply, for example, a maximum, such as this maximum pooling function, the symmetric function, you would just pick a specific point within this area where you have high values. And so in that way, basically what you're doing is this global feature vector just pinpoints specific areas on your object. And so when you combine this with a network, it really focuses on areas that are useful and helpful for your task. So, for example, classification, but it could also be forecasting. So this is in short what this feature representation looks like. Yeah, this is then how you would apply such a maximum, but I think everybody knows how to take the maximum, so we don't have to spend too much time on that. So yeah, so far we have actually talked about a lot of theory and we have not seen a lot of Python, but still we believe that it was essential to actually cover these steps, because these two steps that we've seen, so first aligning the objects, and then the second step using these symmetric functions to actually solve this permutation invariant issue. These are far more essential than showing, for example, a trick where you can deform a sphere into a dolphin. So we thought it would be better also for you guys to actually focus more on this theoretical side, but still as some sort of bonus to still mention a bit of Python. We've seen this Open 3D package. Yeah.
Transformation function that you apply.
Yeah.
Globally over the entire object. Don't you then lose information that is regionally specific?
Yeah, that's a good point. Yeah. So in this way, you actually get a global representation, and especially for classification, that can be really helpful. But again, if you really need specific detail, yeah, you probably need to add more things. So what you can do is, for example, you can add a skip connection layer. So you have information at a lower abstraction level. So you take the output of one of your first hidden layers, you skip connect that. So what you usually also see in segmentation networks, where you add more local context to it. You could apply something similarly, but it's true that yeah, the eventual output by using these symmetric functions is more of a global representation. So you will always lose some information, but that's then with the cost of dealing with this permutation invariance.
Apply it on multiple subsections of the image. You know, like multiple versions of it.
Yeah, that's actually funny because this is called PointNet, and the authors also introduced a new version in which they actually recursively do this. And so it kind of has the same idea as a convolutional neural network, but then you are just directly applying it to points. Yeah, so that would be something to check out for you. So as a last thing, I quickly want to mention this package, which has been published by Meta, so by Facebook Research. So again, this Open 3D package really helps with these pre-processing steps, but if you really want to apply modeling, this package is really nice because it has specific 3D loss functions that have differentiable support. So you can use these to train networks, for example. They also have specific data structures, and they also allow for heterogeneous batching. So if you have, for example, multiple objects that are represented by a different set of points, well, usually if you train a network, your tensors need to be of same size. And so they provide actually techniques to deal with that. And then next to that, they also have this cool example of how you can deform a sphere into a dolphin. So yeah, you could also check that out, of course. So yeah, we've actually provided you now with the tools that you need to start modeling with 3D data yourself. So we hope we got everybody encouraged to work with it and excited. So yeah, now it's up to you to actually start modeling 3D objects and to ask questions if there are still any questions left. But thank you for listening.
Thank you very much. You mentioned that this example is for 3D printing at the beginning, or
Yeah.
how this concept is related to 3D printing.
Okay, so in the beginning, these so-called STL files, they often come. They are accompanied with 3D printing. So yeah, maybe you can answer that.
Yeah, the use case of our client was to they have to 3D print an object, and they have to 3D print the same object in 5 years, and they have to measure again, like they have to go back to measure the object again. In order, it's a bit weird if you don't know the context, but they have to go back to measure it again, and then they can 3D print it. But they want to be able to predict how the shape will change, so they can skip the second measuring part. And that's why it's related to 3D printing.
Yes. But also a lot of data, of course, comes from 3D printing, because these STL files, they also are used for 3D printing. And so you can actually use these STL models, load them into any representation you want. So for example, this point cloud or voxel grid. So I think there's also a connection there with 3D printing.
How much data do you need to train a neural network?
That really depends on the case, of course, and because usually you have a lot of points to represent an object, so you would also need a lot of data sets because you large data set because you also have a like a lot of parameters. So I couldn't really say. Yeah, it really depends on the case, but you would need quite some samples for that. Yeah.
But you need to train the model from the same object data. Let's say that this is a monkey, you need the objects from monkeys only.
Yeah, yeah, but you could also try to add other models, but then you might want to use a bit of different techniques maybe. So, like maybe you would want to use different functions to extract these feature vectors from them, because they can be different, for example. So you could also add more objects, but of course that would make it more complicated. But for example, for classification, you could do something like that. Yeah.
Thanks.
Yes. Yeah.
What did you deliver to a client at the end of the project?
Maybe.
Yeah, this was more of a research part of the project, so I don't think this is finished, and we have to develop that. But we had to, we delivered another part of the project where we had to reverse engineer the monkeys from another data set, and that's something we did deliver. But yeah, that's not relevant to this use case, but this is still in progress.
For let's say the 3D printing, will you forecast if you want to print a shoe? Will you forecast the shoe or the user to grow it, let's say?
Yeah, I think you could do it in both ways. But if you would have the object, I think, yeah, it really depends, because on one hand you can measure the foot, for example, and have like a 3D version of that and try to model that. Or you have the shoe of a user, and then you can indirectly model the growth in a foot, for example. So I think you could employ both approaches there. Yeah.
Thanks. I also used some the Blender API before for generating 3D objects, but I didn't notice that, especially if you're trying to load in external data, that it takes extremely long. So I was wondering how the time consumption was for this.
Actually, I've not experienced any issues with that. I think you also didn't. No.
It's relatively fast.
Yeah. Yeah.
Okay, that's good to know.
Yes.
Yeah, when you were talking about permutation invariance, I thought like, oh, I know where this is going. This is going towards graph neural networks, and then it didn't. So I'm kind of curious. Is that something that you looked into, or reasons why you went this way and not the other?
There's not really a specific reason for that. But if I remember correctly, I think these graph networks have also been used, but then mostly for these mesh representations. Because they have a little bit more information also on the connectivity between points. Then I think these graph networks also make a bit more sense, because you already have this connectivity information. But then for point clouds, we didn't really consider it, because we already thought it was also a difficult case. Also, these graph networks were a bit new to me, so I think it was more of a preference that I didn't look into it. But it could also be something to check out. Yeah.
Great talk, thank you. Following on the previous question, what tech stack do you use for this type of modeling? With it being like neural networks, 3D images, what do you do the modeling on? Like cloud computing, or what's your tech stack?
The tech stack. Yeah, actually for my thesis then, for example, I used Google Colab, but it was quite intensive, so eventually I was kicked from Google Colab because I was using too much GPU. So actually you need quite some computing resources, especially for this PyTorch 3D. No, wait, it's more this side. So for this library, they have a lot of CUDA support, so you can really easily train networks using graphic cards. But then if you just use regular CPU power, it takes quite some time. It takes a lot more time to actually train these networks. So yeah, I did it first on Google Colab, and that worked for me. So yeah. Yes. Yep.
What's the output of your network? Is it a class label or another 3D shape?
Yeah, so again, it depends on the case. If you are classifying, for example, the object, then you get a class label. But in the case of forecasting, the output would be a point cloud. So in that case, if you remember from the beginning, we want to map an untransformed point to a transformed point, and we basically map the difference between them. And so eventually you get them, like these difference vectors for all points. And if you add those then to your untransformed point cloud, you get a whole point cloud representation. So in short, the output would just be the point cloud representation.